about the different, I discussed about the inductor current, different slopes of inductor currents and that averaging of that inductor voltage, okay, over the full wave, over the full switching time period, okay, and finally we will get that expressions of inductor current, inductor voltage. Okay, so average inductor current. So it is your, we can see over there actual waveform of including the ripple, and this is your average waveform of what inductor current. It is there with respect to time. So on time is dts and total time period is ts, means switching time period. And here you can see the average value of inductor voltage level over the cycle, means over the switching period. Okay, so I think I hope all of you just gone through that topics, okay, and you are, I think all of you able to understand that what is that idea behind that concept. Okay, so if you have any doubt you can ask me. Okay, so I hope you are you completed it from your homework. Okay, so then we can go for that next idea, that is your capacitor waveforms. Okay, so like your inductor current waveform, we are also focused about that averaging of capacitor waveforms. Okay, so capacitor waveform means capacitor current waveforms is there. Okay, so if you see that equations, okay, so where was that equations? So we can go back some previous slides, so we can get that idea of that capacitor current. Okay, so for switch on condition, okay, means when the switch is in your position on, means switch on condition, that circuit is for your switch on condition. So here we are getting expression of the capacitor current. So it is ICT equal to C dVt dt equal to minus Vt by R. Okay, so it is your minus Vt by R. Okay, so what we can do over there? Okay, so we can replace, we can write that one. So for the switch on, when that switch is on, means that switching converter switch is on, so what was that current expression? So you can multiply that expression, that is your expression. So what is your average expression? So it is your average expression for neglecting that small ripple. Okay, so ripple approximation, after the ripple approximation you will get that one. Okay, ICT equals to more or less similar to VT output average over the switching time period divided by load resistance. Okay, so it is your Vt and plus minus both are there, and it is your load resistance. Okay, so you can get from there. Okay, so you can multiply that one, you can multiply it with dts. What is your on time? That will be dts. Okay, and what is your off time? Off time is your 1 minus dts. So you can say like that, it is d dash ts. Okay, d dash ts. Okay, so capital D means it is the DC value. Okay, and lowercase italic d means you can consider like that, it has in two component, one DC component, one other ripple component. Okay, you say like that, it is your instantaneous value, you can say like that one. Okay, you can remember for your better understanding. Okay, so here we will get that expression of inductor capacitor current. Okay, so in the form of output voltage divided by load resistance. So here after that you are average that value. Okay, so it is coming like that for on period. Okay, so similarly it will be multiplied with dts for the on period, then off period. So final IC you need to be calculated. No? So for similarly we will get that expression for when that switch is off condition. So when switch is in position 2, so that is your circuit diagram. Okay, so circuit diagram you will get. So IT if is your input, so I am telling about that sign convention. Okay, that's why that negative is there, so you are using the KVL expression, and finally we will get that IC current, means capacitor current in that averaged. Okay, average that throughout the path. Okay, so finally so it will be average with the total time period ts. So vt by r is there, so definitely it will be average over the time period ts divided by r is there. Okay, so small ripple approximations also be applied for this expression. So what will be the expressions for off time, means when you switch is position 2, means off condition of the switch, that capacitor current. Okay, so you can multiply that entire thing, okay, with your d dash ts. Okay, so d dash ts means 1 minus d ts. Okay, so then we can add all of them. Okay, like the like your inductor expression, inductor voltage expression. Okay, so that method we can also follow in your capacitor case. Okay, that like last methods we can directly implement over there. Okay, so here we just that expression with the single in a single equations. Okay, so average capacitor current. Okay, so this is expressions of your average capacitor current. Okay, so here you can see that slope one. Okay, so minus vt by r into that minus vts vt suffix s is there. Okay, so minus is there for that slope. Okay, and here you can see that dt is multiplied with minus vt by s, means not by s, so suffix s. Okay, whole divided by r into dt. I told you now. Or next case that d dash t is there. Okay, so with your the current expression for your off period. Okay, so directly we are putting over there that then we can go for that averaging. So collect term and equate. So d c dv ds. Okay, so here we can find out that one. Okay, so how do you find out it? So you have to derivate that value. Okay, so after derivating you can get that one. So no need to derivate, basically you can also replace that value. Okay, no, derivations is not required. You can replace that expression of vts in terms of dvt dts. Okay, so how to get that one? So that expression is there na. So you, if you know that value, so that dvt rc means what vt averaged over the cycle ts whole divided by r, means that expression is there. Okay, so here, so you will get that minus vt average over the cycle time period ts by r equals to what, c dv dt. C dv dt, that you can replace over there. Similarly that same thing also be there, c dv dt. Okay, only that multiplication factor is dts. Okay, d dash ts. Okay, so here you can replace that value with c dv dt. Here you can also replace those values c dv dt. So if you add both of them, so what is d dash t? D dash t means 1 minus dt. So minus dt plus dt will be cancelled each other. So finally 1 will be there. So finally you will get that expression. Rest of the expression means multiplied with your current expression. Okay, that is there. So minus d dash t into it average through the cycle ts minus vt by r, mane vt average by ts whole divided by r. Will equations. Okay, after that we can put individually. So here we can put that expression individually for first slope, and in case of second slope we just put over there, and dotted line means average, so neglecting all those things. Okay, so finally we will get that average line of your average current of in the capacitor current over the time period ts. Finally we will get it. Okay, so here we can here we'll get that final expression that is coming from here. Okay, so final expression is there, so we can replace that one with the expression of final one. Okay, so finally that is your current expression. Now we can go for that voltage expressions. Okay, so voltage expression, similarly that method is there, y equal to mx plus c from that one. Okay, so what is your voltage expression? So vt, you can send that portion. Okay, so from here you will get that voltage expression. Okay, you just equate. Okay, you just equate that equations. Okay, so we will get that expression of voltage one, or you can replace that value. Okay, so c dvt some with say dv average by the ts or divided by tt, means by dt, so you will get that expressions. Okay, so finally that slope, again the slope will be there like your inductor currents. Okay, so in case of inductor current, here we will get that expression for the capacitor voltage. Okay, basically that capacitor voltage is your state variable. Okay, so in case of inductor current is the state variable, and in case of capacitor, the capacitor voltage is your state variable. So similar method is there for initial condition, but that means that v0 conditions, it will be some having some value. Okay, some value is there, then it will be sloped down and reach to that vdts. Okay, like that way. After that again another slope is there, and finally we will get that vts. Up to that voltage you will get up to vts, and if you add, okay, and if you add them, so that final expression will be there like that, y equal to mx plus c. That expression you can see over there, it is following over here. Okay, so if it is following over here, so and it is a state variable, that means capacitor voltage. That's why for the zero instant you will get some bias value or the fixed value, then it is slowed down. Okay, after that again it will be ramped down, then ramp up. Okay, so two expressions will be there, and finally we will get that dotted line, means it is your average value. Okay, so that Cummings vt, that average through the cycle. Okay, that is your ts. Okay, so that's the fundamental thing we can observe over here. Okay, so after that we will see that average input current. So average input current means what? That all the cases you can see that inductor current is there, and inductor current and inductor current is there, but in from where that inductor current is coming? So it is coming from that your source side one voltage, you are added one dc voltage now. So if you are added some dc voltage, definitely when you are going to calculate that inductor current or the load current or the capacitor current, definitely it having some contribution. So if your source current is not there to your circuit, so how do you get that inductor current? Basically inductor is charged. Okay, so in that inductor or capacitor, both the energy storing elements, they are charged by whom? They are charged by the input side current. Okay, that current is coming from the voltage source, means input voltage source. Okay, so in DC-DC converter, what happen? You are providing the DC in voltage source as a input. Okay, and you are also getting output, it's a DC output. Okay, so it's a DC-DC conversion. So input side DC voltage is there, that DC voltage is responsible for generating that input current. Okay, that current you have to calculate over here. So how much current is there? Okay, so in my last chapter, okay, in chapter 3 means in my last chapter, means before your puja vacation, I have discussed. Okay, so that is your chapter 3 actually from that Ericsson book. Okay, so discussed about the very basics expressions for buck converter, boost converter, buck boost converter, all those expressions. That's why it is written like that, chapter 3. Okay, in the Ericsson book. Okay, so we have found in chapter 3 that it was sometimes necessary to write an equation for the average converter input. Okay, so average converter input, we need to find out the current, average converter input current. So why it is significant? Sometimes what happen in case of, I told in my some of the previous classes, that converter, power electronics converter having two circuit, one is called power circuit, another one is called control circuit. So normally power circuit is decided by the topology of that converter. So what type of topology you are using, you are designing or you are using for that power or the energy conversion. So that topology is decided the steady state nature. Okay, that topology of the converter is decided the steady state nature of that converter dynamics, and controller decided the transient behavior of that converter dynamics. So controller also important, means control circuit also important for controlling the converter and to say to justify the transient response of that controller. of that converter, and your steady state means topology decided the steady state value. So in case of buck converter, buck boost converter or boost converter, all the cases you can see that inductor current, the inductor is charging, okay, over the period, then it is discharging also in period. So on period plus off period you are getting the total time period. Okay, so due to on and off, so you will get some of the charging current and discharging current. At the presence of this charging and discharging current, so that you are also observe the ripple of the converter. Okay, there is an effect on the ripple of the converter. Okay, so that ripple is significant. You can see the ripple is significantly high. Okay, ripple is significantly high means it totally depends upon your slope. Okay, slope of that inductor current. Okay, so normal convention, what happened that inductor is responsible in boost converter to provide that additional energy. So already that DC value is there, DC voltage source is there. Okay, that voltage source is responsible for charging the inductor for first instant. For second instruction, DC voltage plus that voltage appeared means energy stored in the inductor. Okay, in terms of voltage source, okay, both are added and both are to provide that energy to the output side. Okay, so that's why more voltage you can observe in case of boost converter. So that's why, so what you can observe that inductor current is charging, okay, then it is discharging. So overall ripple, okay, so overall effective ripple is comparatively high in case of boost converter compared to the other conventional converter like buck converter, okay, and buck boost converter. So what happens is that ripple, if that ripple, that means delta IL, if that value is high, so what is that mitigating factor to reduce the ripple? So you can change the inductor value. Okay, if you make it more value, okay, so then you can reduce that value of ripple current. But the problem is that if you change that inductor value, so effect to the converter dynamics. Okay, so high value of inductor means your converter, two things you can observe. One physical problem you can observe means physical significance of that converter. You can observe that it will be in bulking nature. So 2 millihenry inductor means it's a very weak size inductor. Okay, and so normally you need to try it by microhenry range. Okay, but definitely there is some specifications. So specifications means it should be below 100 watt, maybe 50 watt converter. Okay, so you can design like that way. Okay, so inductor current you are trying to make in micro henry range. But if you are going for the more value of inductor, so definitely the specification will be different and that converter rating will be high. Okay, so high rating means it may consider it may responsible for additional energy loss. That's why we are going for different topology of that boost converter. So we just switch that boost converter to entirely boost converter. So what happened in case of entirely boost converter? So we are just two boost converters is there. Okay, they are operating in countering mode, means not parallel operation is there. Okay, so when one boost converter, if you consider two boost converter is connected parallel, okay, but their operation is complementary each other, means means when first boost converter is on condition, okay, then second boost converter should be off condition. So totally 180 degree out of phase operation you can observe. Basically 360 whole divided by 2 means total number of boost converter, means total number of phases. Okay, 2 converter means 2 phase converter, 3 converter. Okay, so 80 degree. If 3 boost converter connected in anti-parallel, connected in parallel, but their working convention is like that. 360 divided by 3 means 120 degree apart each other. Their working principle is means when that first converter is on, the second converter will be on after 120 degree. Okay, and the third converter also be 1 after 120 degree of your second converter. Okay, so like that way, like that mode of operation you can see over there. So that inductor current ripple will be reduced. Initially all the inductor having same current ripple, but input current ripple is reduced. Basically all the converter are connected in parallel. So what happened? So if they are connected in parallel, so same current means same input current will be splitted into three part. Okay, so your input current is the addition, means is the resultant of your three inductor currents of your three individual converters. So all the converters in a means compressed in a single way. Okay, so that's why it is called that interlink converter. Sorry, so that's why it is called interleaved converter. Okay, so in normal boost converter what happened, that is your inductor current similar to your input current. Okay, that inductor current you have observed the same ripple content in your input current. So there is no options for switch of conditions current ripple cancellations. But if you connect all the boost converter in interleaved mode, then what happens when one switch is off, then another switch is on. Okay, so another two switch is on. Okay, so then what happens? Then it will countering the output. It will countering that off time current ripple. Okay, so we will get additions. Okay, vector addition of three phase means three inductor current. Okay, that's why that effective ripple will be less, and it is called that input current ripple less means definitely there will be less harmonic content, and input current ripple is less means input side you can omit some of the insertion of that electrolytic capacitor. Okay, normally for reducing that input ripple, so we will add one capacitor across that voltage source. Okay, so then what happens, so some of the current ripple may be reduced. Okay, so that we cannot add. Okay, so in case of, you can see over there, it is likewise that necessary to do this AC model. Okay, so it is definitely important. So buck boost input current waveform is, I took that example in buck boost converter in my previous slide. Okay, so before your vacations, okay, you can go through that slides or you can read the slides, you can understand. Okay, so where is your input current? IG was your input current. So it was that IT means inductor current. Okay, the total current is average over the cycle of TS during that sub interval 1, and it is 0. Okay, when during the sub interval 2. Okay, so that's why you will get that 0 current. Okay, over there. Okay, when sub interval 2. So what is your average value? So you can multiply that IT TS into dt. So basically d dash t multiplied with 0 means definitely it will be 0. So it is plus 0. IGT average over cycle t, then IT means current average over the time period TS plus 0. So you will get that one. It is your average current, and converter input current from nature you can observe over here. So input current having equal amount of current ripple. Okay, so you can see over there it having current ripple. Basically IG it having some value, then it is 0. So definitely there is some current ripple. Okay, also you can that's the problem na? If there is some of the waveform, so the current will not be in 0, so effective ripple will be less. Okay, so then we are using the perturbations and the linearizations options. Okay, so what do you mean by that perturbation? So converter average equations are there. So it is your total expressions for LDI, DIL dt. Okay, that is averaged by the TS. So it is C dVt dt averaged by TS time period. Okay, so equal to what? Dt into input voltage Vg within bracket T and average by time period Ts plus d dash T within bracket Vt average by time period again Ts. So I think all of you are able to understand that expressions. Okay, so similarly for it is the expressions for inductor voltage, and C dV dt it is expressions for capacitor current for a buck boost converter. So here we can observe that expressions multiply of dt is d dash t, and here both the this expression is present for off time as well as on time. That's why there is d plus dts. Okay, d plus d dash. Okay, d plus d dash means is the 1. Okay, only ds is there, and input current value is dt into it average by total time period ts. Okay, I think you all of you able to understand that expression. So it is non-linear because of that multiplications of time varying quantity that I told in my very basic slide. So why it is non-linear? Non-linear because it is a time dependent component. It is not linear LTI system, linear time invariant system. It is not an example of a LTI system. So all the quantities you can see over there, your duty cycle. Okay, so inductor current, inductor capacitor voltage, input current, all having that expression is time varying multiplications with your time varying component, that is your dt. So with other time varying quantities such as it and vt. Okay, so all are having the time varying component. So due to presence of this time varying component, these converters are the examples of your these converters are examples for your non-linear converters. Okay, so due to presence of some time variant components, okay, in the differential equations. Okay, so construct the small signal modeling. Now the concept of small signal modeling is coming. Okay, so what happened, the you have to linearize about the quiescent operating points. Okay, quiescent operating point means that I told you that what is your quiescent operating point in my previous slide. You can see over there for very basic that is your quiescent operating point. Okay, so it is your quiescent operating point. Okay, that I discussed over here. So at that point, so I told you na the expressions of changing of duty, and it appears output voltage. So you can see at 0.5, at you will get some of the operating point, and that value is minus Vt. Basically that changing of duty with your voltage is in buck boost converter. It is an example of a from a buck boost converter, highly non-linear. Okay, so you have to find out one point. Okay, that point you have considered as zero point 0.5. Basically at 0.5, what is that expression? D by 1 minus d. If that value of d is 0.5, so we will get that d by 1 minus d is equal to 1. So at that value you are considering that it is a linear point, and that point is known as quiescent operating point, and you are making the slope and draw the slope for linearizing that function. So you are considering, so why you are putting the slope? So you are considering point, and here you can see it is your actual non-linear characteristic. So non-linear characteristic means the rate of change of your independent variable and the dependent variable. What is your independent variable? Those variable is plotted in your x-axis, so it is an independent variable, and those variable is dependent means your y-axis is a function of x. Y equal to f of fx means y is a function of x. So you can say like that, y is dependent, y-axis variable is dependent on your x-axis variable. Okay, so the rate of change, you just listen my point, the ratio, okay, the ratio of change in your x-axis variable and the ratio of change in the ratio of change in x-axis variable and that y-axis variable, it should be constant over that zone for the linear operations of that converter. If it is varying, so you can say like that it's an example of a non-linear. So this point you can see that the rate of change of your x means the duty, and the rate of change of your voltage is your output voltage. That value that is not valid with that point. So okay, so basically that uneven changes are there. So it's an example of a non-linear characteristics. Okay, so you are going to be linearize the equations. Okay, quiescent operating point at d equal to 0.5. Okay, so it is your static control to output transfer function, control to output characteristics. Okay, so from here you can understand is quiescent point. So I think that is given. So construction of a small signal model linear is a quiescent operating point. So you have to find out that point. So linear point, and at that point you have to consider that some steady state value. Okay, at that quiescent input. So your dt Okay, so that value of, I told you like that instantaneous value is look like instantaneous value. So what is your fixed value? So steady state value is capital D, and VG average with the total time period TS. So that is your capital VG. So you can say like that capital value means it's your DC value. Okay, now analysis for inductor current. Okay, inductor current, capacitor voltage, and input current. Okay, so why is it inductor current? So you can say like that IT average by TS, VT average by TS, IG average by TS. So you need to find out the value of V. So what is your output voltage V? V equal to minus D by 1 minus D into VG. It's the expression of buck boost converter. You know that expression. D dash means 1 minus D. Okay, so D minus D by 1 minus D into, why this minus? Minus basically we are in the slides we are considering that buck boost converter polarity is different. Okay, so we are considering plus minus polarity, but not we should getting in buck boost converter minus plus polarity, means minus output voltage, means reverse output voltage. So in this expression, so making it reverse, so you have to put one negative sign over here. Okay, and then you are getting that steady state inductor current. So what is your steady state inductor current? It will be minus V by 1 minus D into R. So directly it is coming. So here we are getting that quiescent value, that is the quiescent value. It is all at the steady state. So I, V and IG. Okay, given the state analysis. Okay, so what is your input current? IG. IG equal to D into I. Okay, so all are in steady state, that's why they are in uppercase conditions. Okay, then we can go for the perturbations. Okay, so then total average values are there. Okay, so VG is your average value. VG, it will be average with the time period TS, and it having some DC value, or you can say like that constant value, that is VG plus that VG cap, means it is, you can say like the small variations is there, it is your AC value. So let us assume that input voltage and the duty cycle are equal to some given DC quiescent value. So it is your some DC, some given DC quiescent value plus, so superimpose small AC signals variations, means you can say that is your bias value, means steady state value plus it is your ripple value, you can say like that. So your total average value equal to, similarly for your it is input, VG means input voltage. Okay, so DT means your duty cycle, again it having some constant value plus some of that small variations of that voltage also be there. Okay, in response and after any transient have subsided and subsided, then the converter depends upon that voltage and the current will be equal to the corresponding quiescent plus small signal variation. So we just add like that way, we just add those one in that manner. So what is your IT? So IT means your inductor current. So IT is average over the cycle, over the time period, switching time period, that is your TS equal to what? I plus within means it is your AC component, it is your DC component. So I is your steady state value plus AC component I cap T. And again, so for capacitor voltage same thing also happen, V plus V cap T. IT equals to same, so IT equal to TS plus IG plus I cap G within T. So we can go for that way. So that is called the perturbation. Perturbation means if we having some nonlinear components, okay, so we can perturb, okay, we can split that components or split that variable into two parts. One is for DC part, another one is for AC part. Why we are going for that? So we have to calculate the transient values as well as some steady state value. So then if we perturbate all those things, then we just put all this VG instead of VGT average over cycle TS, we are putting VG plus VG cap T. Okay, then what happened? We just replace all those expressions in our previous equation. So previously we have considered the example of a buck boost converter, and we having some expressions. Okay, for the state equations we are having, means when position 1 the switch is position 1 means switch is on. So we having some set of equations, differential equations for inductor current, for capacitor inductor voltage expression and that capacitor current expression. Now we just replace all those average value by its the steady state value plus AC value, means VG plus means DC value plus your small variation value. Okay, then we can equate. Okay, then equate and eliminate the, after eliminating all those values, we will get some of the equations. If we get the some set of equation, now what we can do for left side and right side. Okay, so it's an example of an identity. Okay, identity. So what we are doing with that identity, so we can in case of complex number example, what we can do, so we are comparing the real numbers and we are comparing the complex numbers, then we are getting that value. So similar thing also happen for these expressions. There is no complex number, but it's an example of identity. What we are doing in identity, we are equating all the left hand side x component and x right hand side x component. Okay, then all the left hand side y component and all the left and right hand side y component, like that way. So we are equating. Okay, so like that way, now we are replacing all those values with our expression. So that you can see that comparatively, if you see that what is called small signal as assumptions. What is the small signal assumptions? Where we have observed that mod value of VGT, okay, it definitely very less than of your VG. Basically you are approximated, na, so that ripple voltage is very less, okay, compared to your DC value. So that's why you can neglect that AC value. Okay, so if the AC variation are much smaller in magnitude than the respective quotient value, okay, the respective quotient value, so what will be that expression? VGT within cap, it is very less than input voltage. Similarly, duty, that small AC component of the duty, it will be also very less than your main duty cycle. Okay, means DC duty cycle. Then that inductor current, so ripple of that inductor current is very less than of your main current. So similarly, that output capacitor voltage also very less than of your the output voltage V. Okay, IGT also very less than of your input current IG. Okay, that we can approximate it. So sometimes we can neglect over there, but in case of Planck transfer function of the converter, Planck transfer function means control to output transfer function of the switching converter. Basically, for controller designing portion, we have to convert the nonlinear converter equations to the linearized means LTI equations, means LTI means transfer function. So for the buck boost converter, we having lot of set of equations, state equations. So we can convert those set of equations in the form of transfer function. Okay, that is the basic motivations. Okay, then we can go for the designing of the classical controller. So in my next class, I will discuss that all the transfer function of the classical converters. Okay, and I will show you that expressions. So derivation I will show you for buck converter, boost converter, and buck boost converter. Okay, and their transfer functions. So okay, so that I will show you in my next class, means tomorrow. Okay, then the nonlinear converter equations can be linearized. So after that, we can linearize the nonlinear converter equations. Okay, then you are putting so perturbations of that equations. Okay, perturbation of that inductor equation. So insert the perturbed expressions with the differential equation. So we have some of equation L di dt plus d Vg, okay, plus like that we are replacing those values. So if we have that expression, so that was your expression L dil dt plus like that way. So now your L is constant value, no need to change it, but it will be replaced. That it will be replaced by what? It will be replaced by I plus that it. What is the expression of it? I plus I cap t. So that I t will be replaced by I plus I cap t. Okay, that dt, what is the expression of dt? Dt expression is your d plus d cap t. So d plus d cap t, it will be replaced. Vg, what is that expression of Vg? Vg is Vg, capital Vg plus cap Vt. Okay, so it will be replaced again d dash t. What is that expression? D dash t equal to definitely coming d dash plus d dash t, cap of d dash t, like that it will be replaced. And Vt, again that expression of Vt will be there. Expression of Vt is V plus V cap t, that we are replacing. So all the thing we are replacing like that way. So finally we will get that expressions. Okay. Now note that Vt is given that what is d dash t? D dash t equal to 1 minus dt. So you can replace that value of dt equal to 1 minus capital D plus of d cap t. So it is coming d dash minus d cap. So with d dash equal minus t. So you can replace that value. So now you can make it derivation. So derivative. So dit dt. It is what? It is your constant. So L it is capital dt plus d I cap t dt plus this is your dc terms. Okay, so vg you are getting. So okay, so all the first order ac terms in linear, and it is your second order ac terms that is non-linear. Why it is non-linear? Basically two variables, okay, two time variant variable are multiplying each other, so you can say that it is non-linear component. So now it is your constant value, so you are making it 0. Okay, now your dc component is there, first order ac component is there, it is your non-linear component. So multiplied out and collected the terms. Okay, then what happened? Then perturbate in inductor equations. So you can equate that equation. So that expressions is that expressions are there finally. So what you have observed over here, since I is a constant, this is so derivative of the constant value is always 0. So it is your expressions, final expression. Okay, so that is coming from here. The right hand side contains three types of terms. Okay, that right hand side it is contains three types of terms. So one is called dc terms containing only dc quantities. So steady state values are there. So it is your dc terms. Okay, dc term means only the steady state value. Okay, so it is your steady state value. That's why it is called dc term. Then the first order ac term. So it is your first order ac term. Okay, contain the single AC quantity, usually multiplied by the constant coefficient. So it is multiplied by your constant coefficient. Okay, such as the DC term. Okay, so constant coefficient such as a DC term. In DC case, what happened? Your DC term means your DC term is multiplied with only DC terms. Both are DC. Okay, but in first order AC terms, you can observe that your D capital D is multiplied with the small variation of your VG cap T. Okay, so all the cases you can see like that. So one constant value, another one is the single AC. So it is subtraction of two constant value and one single AC component. Okay, so there is a linear function of that AC variation. So if time is varying in linear condition, your that VG value also be changing with that respect of time. So though it's a function of time, but it having linear variations. Okay, but if there is a multiplied with two things, okay, dt is multiplied with d cap t is multiplied with your v cap g, and d cap t is multiplied with your v cap t, then what happens? So it is second order equation, it is second order AC term. Okay, and it containing second order AC term and it containing, so you can say like that, it is second order AC term. Okay, so it is your second order AC term, so it is non-linear. Okay, and containing the product. Okay, the product of AC quantities. So two AC quantities are there. Okay, so these are highly non-linear. That's why it is called non-linear, because of involve of multiplications of AC quantities. Okay, multiplications of AC quantities. Now you can say like that, if that your V cap T or any cap product is very less than of your DC term. Okay, so multiplying of the two small component, okay, like 0.01 component is multiplying with your 0.001 component. If you multiply both of them, so after multiplication it will give very less component. So you can sometimes you can neglect them. Okay, so that also happen. Okay, that is written over here. So neglect the second order term. So why we are going to be neglect? Because of that very less term. So if your VG, okay, V cap T is less than of your VG, less than, not only less than, very less than of your VG. So D cap T means duty also very less than of your D. So I cap T also very less than of your I. V cap T also very less than is V. I cap G also very less than IG. So if you multiplying that AC component with other AC component, so definitely that will be less than of your DC component. That is happened. then in second order AC terms are much smaller than the first order term. For that example, d cap t into v cap t, v cap g is very less than of your b into vgd. That is happened. Basically, it is your DC value. DC value having significant amount of value, it is multiplying with the sum value, but this is significantly less with this term. So when mod of d cap is very less than of your d, so we can neglect the second order term. Also the DC term of the each equation side are equal. Okay, so more or less these two are components are equal, but the second order nonlinear term you can directly neglect it. Okay, so then we are linearizing that equation, so finally we will get that expression. We can omit this point. Okay, this equation we can omit it. Finally we will get that expression like that. This one we are getting, so d we are common, we are getting d as a first bracket. So what is that equation? So if we take d as a common, so it is coming vg plus within bracket v cap t. Okay, and d dash we are taking common, so we will get that v capital V plus v cap t. Okay, plus vg minus v within bracket d cap t. That is coming directly the expression of inductor current. Sorry, the expression of inductor voltage is there. Okay, I think all of you able to understand. So there is no such any confusion. Okay, so upon the discarding the second order term and remove the DC terms which add to 0, so with the left of them, and this is decided the result, the linearized equation we describes that small signal AC variations. Okay, so that's why it is called small signal analysis. Okay, so know that the quotient value, that capital D, capital D dash, capital V, capital Vg are treated as given constant in these equations. Okay, so here they are behaving like a constant in these equations. That's the basic motivations. Okay, then we can go for the same thing for that capacitor equations. Okay, so we're having some equations like that. Okay, part of it that equations. Okay, so it is your generalized equation, then we are putting that one. So dc vdt again it is 0, so that having dc component. Then similarly first order AC component it is linear, second order AC component is non-linear. Then we are neglecting that second order term, finally we will get that expression of capacitance. So it is described that small signal linearized capacitor equations. Similar manner. Okay. So then average input current, same thing, three equations are there. So one for inductor voltage, second one is a capacitor current, and third one is the input voltage. So first two we have completed. So secondly we are third one, it is for input expression of input current. Okay, that we are doing. So DC component again input current Ig equal to I cap G. Okay, Ig plus I cap G. So it is DC term, it is first order AC term, it is equating DC term, first order AC term, and second order nonlinear term. So that term automatically neglecting. So what is your expressions of AC component? So first order AC I cap G equal to coming D into I cap T plus I into D cap T. That is compare. So where it's an example of identity. It's an example of an identity. So we are comparing the DC term with your DC term. So Ig equal to D into I. Okay, so D is your duty cycle and I is your inductor current. Okay, so after neglecting the second order term, so DC term both sides are equating, then first order term is coming, then this is the linearized small signal equation which describes the converter input port. Okay, so I think all of you are able to understand. So finally we will get that expression of construction of a small signal model, equivalent circuit model, and linearizing the small signal model we will get the expression of inductor voltage, capacitor current, and input current. So that is called small signal model. Okay, so because of this I cap T, okay, that is very small compared to your DC value. Okay, so V cap T means output voltage or capacitor voltage is very small compared to your capital V. That's why it is called small signal. Okay, so that's why it is known as small signal analysis. So all the components we are getting, that is small signal equations. So we will get the small signal equations from our state equations. Okay, That's our basic idea. So we can draw this diagram. Okay, small signal, if we get this one, so we can draw these expressions like your KVL expressions. Okay, so we can draw these circuits. Okay, so like simple one you can draw it, so it is your homework assignment. Okay, so you can draw this circuit for inductor voltage. Basically I have almost 10 a.m, so my class is going to be complete, so that's why I'm quite hurry. So you can get the expression of inductor current, small signal inductor current, and how that one. So KVL equation is explained, so I think all of you are able to understand the circuit. Okay, for that inductor voltage. Okay, so how do you explain that inductor voltage in the circuit form? Okay, then the capacitor node equation, so KCL. Okay, so again it is capacitor current na, so KCL you can use. So how it will be look like that current source. Okay, there is a current source because IT means it's a current source and DT. Okay, so all of the current source, the outcome is your current source. Okay, that we can understand from there. Okay, so the equations, so finally that input current equations. Okay, mode equations, finally we'll get it, and we can put the complete equivalent circuit for individual collected 3 circuit. It is individual circuit for capacitor current, inductor voltage, and it is your input current, then inductor voltage, and last one is your capacitor current. Okay, so we can add all of them. So it is your I cap T, both of the cases common, that is only D, it is only one. So you can say like that it's a transformer, like you can see DC transformer. Okay, so that 1 is to D. Okay, 1 is to D. If you multiply it 1 by D with that, so you are getting only IT. Okay, like that it is 1 by D, so 1 is to D. So second here you can get it D dash VT. Okay, and you are getting that D dash IT. Okay, so you are getting, so D dash is to 1, the turns ratio. So you are getting that expressions. Finally, you can say like that it is small signal AC equivalent circuit model for buck boost converter. So replace the dependent source of that ideal DC transformer. Okay, so same example, same method you have to use for buck converter and boost converter. So tomorrow when I will start my class, I just ask all of you individually. Okay, that all of you completed this one for buck and boost converter. That is your homework for your tomorrow classes. Tomorrow when MP Madam class will be completed. Okay, so after that my class will be conducted. Okay, so that is your example for tomorrow class. I think if you are able to understand my all the steps, so you will able to solve the numerical, able to solve the mathematical steps for small signal modeling for buck converter and boost converter. I took that example for buck boost converter. Okay, so thank you for today's session. I think all of you able to understand that how we are going for modeling of buck boost converter, that means small signal modeling for buck boost converter using the state equations. Okay, so